Alright, rolling a pair of dice twice. What's the probability you roll doubles on the first and then a sum greater than 8? So this is AND probability. Is it independent? So if you define your events, you can write it as P, A, and D. If not, you need to write what they are in there. So this is just multiplying the two. And how many ways can we make 8 as a sum? 10? 15? A sum greater than 8, so 9, 10, 11, 12. I don't have that memorized, so it's 10, okay. Okay, if we simplify this, 1/6, and then what is that? 5/18. That helped a little. Okay. And as a decimal, .046. Right, when can you use the multiplication rule for compound probability? If the events are what? Yeah. If the events are independent, and let's say and, because if it's or, we're not multiplying. Alright, 63% of people chosen at random wear sneakers. What's the probability that these random 2 students are wearing sneakers? So, first of all, are they independent? Most likely they didn't call each other and figure out what they're wearing. So we can just multiply 0.63 times itself, or square it, in other words. And we get 0.397, so 39.7%. What percent is this, by the way? Yes. And the probability of flipping 4 tails in a row. So you saw some problems like this yesterday. This is a good one to just write out the outcome. Well, what's the probability that it happens once? And so we're doing it 4 times in a row. This is independent, so we can use the multiplication rule. And so this is 1/16. Or, what is that, roughly? 6%, 6.5%. Okay. How'd that go? Are you on a good path for doing well in this? Okay. Well, good. So far we've talked, in terms of big broad categories, we've talked about or. And for or, we have to ask, is it mutually exclusive? And then if it is, we can just add the 2. If it's not, we have to subtract off the overlapping, or the double count part. And then if it's and probability and it's independent, we can just multiply. And probability, I don't have it up here, but what's the general formula for probability? Don't look, just remember. Don't say it. I have 1. Let's get some more hands up. 2, 3, 4, 5. So general idea behind calculating probability. 6, 7. Alright, that's all of you. Most of you. Go ahead, since you had your hand up first.
The interest in what you're trying to find opens up to a possible.
Good. Yep. Alright, well let's grab that packet now, the green one, and we'll take some notes today. So we're going to talk about conditional probability. I I introduced this yesterday, and we'll have basically two big ways to do this. One, and probably the more common way, will be in a table, but also we'll be doing this with an equation too, or a formula, another formula. So conditional now means that, well, what does conditional mean just when we say that word? Like not in math, but just in everyday life. What does that mean to you?
Depends on what you do to it.
Yeah, that's exactly right. It depends on something now as to what might happen, right? So this is no longer necessarily independent, and we can actually use some stuff in this section to check for independence. So that'll be helpful. So we looked at this weirdly worded question of 85% of all senior girls and 65% of all senior boys attended some dance. 20% of them won a prize. The big focus, I put a star here because we need to do it, but the big focus was this. If you knew whether the selected student was a boy or girl, would that change your probability? And we said yes. Why? Yeah. It was not an equal percentage. Okay? Alright. So make up total. This is just a help to calculate this. It says, assuming the number of senior girls at this school is about equal to the senior boys, estimate the probability that a randomly selected senior won a prize at the dance. Okay? So it says make up total numbers of students and use them to estimate. So roughly equal. Let's just do like 100 girls and 100 boys. That makes it exactly equal. How many girls went? Okay. Yeah, and then 65 boys. So, what is that, 150, I think? 150 students attended the dance. 150 senior students, I should say. So what's the likelihood that a senior won a prize? Like we don't know how many other grade levels went. And honestly, I suppose it's 9th through 12th, but it could be 10th, right? We used to have that Fruita Monument. Was only 10th through 12th. But anyway, 20% won a prize, it says. Of all attendees, 20% won a prize. So what's the probability that a randomly selected senior won a prize? How many seniors potentially won a prize? Well, what's 20% of 150? Can you do that in your head? It's really this. 15, if you want to think of it in an easy way. 15 times 2, and then move some decimals around. Alright? So, 20% is 0.20, but this is 150, so that has one of those zeros. So it's safe to just move it once and multiply by 2. So it's something I feel like that you should be able to do is percentages, quick percentages in your head by multiplying. And I said, like this one, 15 times 2 is fine, but what if it was 1,500, like 20% of 1,500? So when I said move some decimals around, the goal is to be able to do this with mental math. Get the 3, right? 2 times 15 gives you some kind of a 3, and then move the decimal where it's reasonable. So what is 20% of 1,500? It could be 300, right? Let's do a couple more. There's another way to do this. 10% is just move the decimal once. Because that's the decimal place, so just move it right? So that's 150, and then double that because we have 20%. So that's another strategy for this. Let's practice a few more of those, actually. Percentages is definitely gonna. I mean, you probably already have needed to use percentages in your life, haven't you? Like in the real world, I mean. Do you ever shop? Yeah, that comes up a lot. You guys know the tax rate in Grand Junction? Sales tax? Yeah, that's for sure. It's right around 8.52%. Yeah, it's pretty high. Okay, so let's try this. What's the sales tax? And we're gonna ballpark it, because when you're standing there or you're buying stuff and about ready to pay, it's nice to know how much this is gonna add to your total. Actually, I do this online a lot. Like comparing prices various places. I want to know how much the tax will be, because in certain purchases it can add a lot of money, right? Like let's do this. Let's say of $2,000. How much tax are you going to pay? Get there, like ballpark it.
It's like 200.
I heard 170, 180 something. Okay? So we're in this neighborhood of 170 to 190, right? How do we do this for real? 0.0852 times 2,000. Okay? So, you see how we kind of had an idea on that? Good job, by the way. $170. That's a lot. I mean, that's significant to add to that, I think, right? All right. Let's say you're buying a shirt. Actually, let's say you're buying a new outfit. $110. Pants and a shirt.
Only for $110? Are you buying these at Ross?
Jazzy shops the high life.
I don't know, that's like roughly what 511.
Jazzy just bought one sock. Okay? How much is she gonna pay for that one sock? How much tax, I mean?
$8.08.
Yeah? $9 or $10, right? So there you go. Your one sock is almost $120, Jazzy. All right. If you can do 8.5, you can certainly do 20, 30, 40, 50, right? Much easier to do those. What's 40% of 110? $44. Exactly. How? What's 10% of 110?
11.
And then times 4. Okay, so if you had a 40% off sale, how much would her sock cost?
$9 less.
No, $44 less.
Yes.
What'd you say? $66. Man, that's a good deal on your
That's
sock.
a really good deal. Might buy 2 socks.
Yeah, you could get the full pair now. All right, we're gonna move on from this. This is a big deal right here. Okay. So we talked about this table, but let's get into it a little bit more. So the context behind this, they're trying to form a committee for how after-school activities will be funded, and the committee members are selected at random from current club members. And then this is, I told you it's a two-way table, two-way frequency table, or frequency table. There's lots of names for that. And it shows our current club membership data. So reminding you yesterday, we had totals horizontally and vertically, and then we had this overall total in the bottom right corner that should be the same for both the horizontal totals and the vertical totals. Everybody remember that from yesterday? Okay. So, you'll be given some of these where the totals aren't filled out. So now you just know that you add vertically and horizontally and double check that the bottom corner is the same. And then, like I had here a second ago, we can ask all sorts of probabilities. So senior, you would just take the overall senior count, drama, the overall drama count, and then we start asking various other things. None of that so far is conditional. All these probabilities are just straight probabilities that we've seen already, okay? So when we get to conditional probability, let's read this. It's the probability that some event, we'll call it B, will occur given that event A has already occurred, or that we know about event A occurring. That's what makes that conditional, and we use this notation to show that, okay? So we're going to have this vertical line in our parentheses now, and we'll write this down in a second, but B is what's not happened yet. I'm going to shorthand that. And the second letter already happened. Okay? Let's do an easy one. I draw 13 cards out of a deck, and they're all hearts. That's event A. What's the probability that I will draw another heart? 0. Okay, so knowing that A happened changes the probability for B, because I pulled all the hearts out, so now it's 0. That's the idea behind this. If I know something happened that affects the other thing, then I can adjust my probability accordingly. This is how it will look in these tables. And you'll make friends with these tables pretty quick. So let's just pick one. What's the probability of being a senior given that I'm in the art club? So again, the second description, the second event already happened, which means I need to look there first. So I know that this student is in the art club, which means I am only looking at the art club column. What's the probability of being a senior if I know that they're in the art club? 18 out of 58. Okay? Because I'm only looking at art club students. So it's just that group. Okay, let's go the other direction. What's the probability of being in the science club if I know that the student is a sophomore? So what is the known category? Sophomores. So I'm looking just here.
So it's 9 out of 30.
Okay, so 9 probability of science out of 36 sophomores. Okay? So you can just see right in those two examples why this is two-way, right? Good. How is that conditional? Let's just make sure that's super clear. Those last two problems that I just wrote at the top there. Why is that conditional probability? How is it different than the ones down below? Like, what is the condition that's changing our probability? Is my question. Yeah, brother?
It's changing the total.
Yeah, good.
So it's only the total out of one column instead of one.
Okay.
It's like you said, it's the total, and we know that hey, if you're a sophomore, we don't need to look at the junior, senior as well.
Okay. And we run into this all the time. Like, what's the probability of being a senior at our school? Ballpark. Huh?
25.
25%? If I just pick some random student? 58? Oh, 15. It should probably be less because there's fewer seniors in other grades here. Yeah. So, but let's just say like 15 to 20%, a random student I pull out of the hall is a senior. Okay, if I go to an Algebra 1 class, like next door, what's the probability that a random student is a senior?
Lower than 1%.
Yeah, it's really small. So that's this. Like, we know that probabilities change as we change the circumstances, right? So if I adjust the conditions for which I'm looking at probability, the probability has to respond and change to that. Okay, good. Any questions on notation? Again, we'll write about it, but let's look at another version. So same table, same everything. Okay, we have the table method, which I just showed you. By the way, here's a question. What's the probability that a member of the art club selected at random is a junior? So we haven't done that one yet. So P, you guys tell me this time what goes here and what goes here.
Art is M.
Do you guys agree?
Yeah.
How do we know that that goes second?
It's pronounced first.
Yeah, Nate? This is the known thing, right? So we know the student is in the art club. Okay? And then, of course, this time a junior. We don't know that one. All right, looking at the table, what probability is that? 16 out of 58. Okay, so we set the second, in our parentheses, the second word or second event sets the category, and then we're looking just at the juniors out of that. Okay? All right, well, let's do it this way. This is the formula version, and you can see the same notation, B given A. That was this same thing over here. What's the probability of both? So probability, what is B? Junior and in the art club. So in fact, let me write that out here. Junior and art. And then what's A? Alright. So this gets, I mean, you're going to appreciate the table after we do this, but it's equivalent. It's the same thing. What's the probability of being a junior and in the art club? 16 out of 115. Okay? What's the probability of being in the art club? 58 out of 115. And the 115s cancel, and this is 16 out of 58. What?
What?
That face, it looks like you're about to choke. If you do this on your calculator, you'll want to put parentheses around both of these so that it keeps track of things for you correctly. Okay? I see some of you doing it on your calculator. I feel like you don't believe me that that's the same. How do you divide fractions? Uh-oh. We said this. We did a review. What's the rule for dividing fractions?
You have to like flip them. Switch.
Keep. Change.
Oh.
Flip.
Probably not, but
What happens to these two guys?
cancel out.
Okay. So it's just fraction division.
Actually.
Both would use
They're both the same. All right, so you have now two ways to calculate a conditional probability. Now, one thing to note, both of these depended on the table. So what if we don't have the table? Like, what if I just said, what's the probability of, I don't know, getting a speeding ticket given that you own a red car? Well, we don't know any probabilities, so how do we answer that, right?
Is the distribution
Are you speeding?
Okay. Huh?
Are you speeding?
Am
Is
I
there
speeding?
Cop warnings? No, I'm saying these are the things that.
Oh,
Is there like cop warnings on the road?
what's a cop warning?
Do you know what a cop warning is?
Like a speed trap thing?
No, like
No,
on your Google Maps it'll say, hey, cop warning up ahead.
Yeah. And so
How is
There's
that?
a cop.
I never do.
you do that or
Alright.
just go for 100 miles.
So let's read this warning. These are not the same probability. Okay? Even though all the letters are the same, just switching the order actually changes the numbers, which changes the probability. So this is using language of prior events. We've said known event. So make sure you know the one that's after the line is the known, and so that can change your numbers. Actually, kind of a lot. All right, let's try a couple more with the same table. This time, don't shout it out. Just raise your hand and you know. It's probably, well, can you see it?
Yeah.
Let's see if I can make it bigger. No, I cannot. Not without moving. That's just this. It's just ugly. It says sophomore line drama. So just raise your hand when you can tell me.
Why is equal sign so big?
I just didn't quite get it big enough. That's why. Okay, go ahead and say. Good. I heard a wait, what?
Oh, no.
Okay.
I was looking at the wrong one.
Okay, let's do this one. Which is the if we call this AB, this is BA now. So it's the reverse. Okay, what is it?
12. It's 336.
Okay, so 3/17 versus 3/36. This is half as much. A lot different, right? Just by switching the words around. So be careful how you read these. Let's take some notes and then come back and do a few more of these. And then we'll talk about this one. I think we can get through them pretty quick. All right, so this is a new question, isn't it? We had or and first. Now what's this question going to be?
Wait.
No versus no.
Okay. I'm going to call it. Do you have what? I don't think this is going to fit.
That's three. I'm not sure.
All right, conditional. Yeah, and so what we're asking, you guys kind of said it, like, do we know something already occurred? Ability. There we go. So knowing one event occurred changes the probability of a second event. So I want you to start thinking about how this relates to independence. We will use this to check for independence, this concept. Any thoughts at this point? Yeah. Thoughtless. If you pay $110 per sock, you're thoughtless.
That'd be too expensive.
Did you
I
say
had
you
nothing
were
in my
going
mind
shop
until
for
like before this.
For pants and a shirt?
like Walmart?
Where do you shop for that?
Guess or like Apple?
There's still guest stores.
My shoes.
She's
I
just,
love Guess.
she's just taking a guess.
I love
I guess
Guess.
it's at
Hey,
Walmart.
Mr. Evans,
Yeah.
where did you get your 5'11" pants? Did you just order them online or?
Yeah.
Oh, okay. Do you know if they have any that's 38 long and like
Yeah, I'm sure.
32 waist?
I bet maybe.
Okay.
Alright. So we know something occurred and that changes the probability of a second event. That's the big idea. So let's talk about notation. Which event do we know? Yeah. Huh? It doesn't matter. We're going to write both. Yeah.
B is not this
So the second one is the known event. The first one is the event of interest. And you guys, we use this phrase or this word events, but just a second ago we were talking about sophomores and art club. And so it doesn't sometimes register as event, right? Just make sure you're tracking with that terminology, event, that kind of stuff. And then I want us to say what this line means. So it says given that. In fact, let's write out the whole thing. Because this can be kind of confusing. I'm going to abbreviate probability. What is the probability of A given that B has occurred? Okay, put this reminder in a frequency table. The second category is the denominator. Alright, we're going to write two more things. Okay? P, the probability of A given B is not the same as B given A, so be careful. And I made a little heart on my exclamation completely unintentionally. And I realize some of you are like me and at the bottom of your sheet, but I do want to put the formula for this as well. And we'll put a box around it. How do you think this changes if, hold on, there we go. How do you think this formula would change if it was the reverse B given A? What changes in the other side? Yeah, Ryan?
That A would be the denominator.
Yeah, it would be P of A now, down here. Right? Any questions on any of the notes? Yeah.
So, on the second side, where it says P of A and B, if it were switched, the notes necessarily have to be switched? Because we're just multiplying.
Like B then A?
Yeah.
No.
Okay.
Okay, be careful. You just said we're multiplying. That's
No.
only if these are independent, right? Okay. So yeah, let's actually add that caution there.
I was just spelled my name right, but I think you put John in there.
We'll take it off. That's too bad. You write it on every paper. They should learn. Okay. So, Diego's wondering whether the amount of sleep he gets is related to the amount of coffee he drinks. So he's recording cups of coffee and hours of sleep. So, based on this data, what is the probability of, I'm not going to say it because that gives it away. So round your answer to the nearest whole percent. So what's our category in this first one? 6 hours. And then probability of 2 cups is 13. So this is 13 out of 27. And then
Vegetable carbs is about 22.
alright. Go ahead and do that one. Okay, so this time the category is 1 cup, and we're looking for specifically 7 hours, so 9 out of 26. Which is roughly what? What was it? 36? Is that what you said?
I said 26.
I thought I-
Maybe, I don't know.
What do you mean you don't know? It's just 9 divided by 27. Sorry. 20.
26. It's roughly around like 35%, 34%.
35. What's the rounding rule?
700.
Multiply by 10.
Take away a little bit.
How do you round that to the nearest whole percent, it said.
You would
Put the 6 over to the 4 and then move the decimal.
Move the decimal. Now it's 34.6. 5 and above, give it a shove, right?
Yeah.
So this is 35% nearest whole. Are we good on that?
Yeah.
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 I just looked at the notebook.
Oh, okay. Alright, cars. This table shows the vehicles in a parking garage one afternoon. Now we have to read a little careful because B and A are defined, or B and V rather, are defined up here. So B is black vehicle, V is van. So it says, are the events B and V independent or dependent? So first of all, I asked you this a few minutes ago. How does conditional relate to independence? Think about it.
It's one and the
You're saying it's either conditional or independent? Okay. How could we use our ideas of conditional to check for independence? Well, let me ask you this.
Oh, there's only 3.
What's we're doing dice, okay?
Alright.
So we're going to do a super simple one. What's the probability of rolling a 2 given that I rolled a 3?
Oh, that's.
It's the same.
That's
Does knowing that I rolled a 3 change the fact that I'm about to roll a 2?
No.
No.
So, in other words, just because I know, in this case, just because I know something doesn't change the probability. So does that help you think about how we can use this to check for independence?
Yes.
Okay? What could I write on here that would tell us whether it's independent or not? Like, how would you modify what we've done or add to it?
You would just do the same thing, but take off the roll 3, so then it's just, so you would do what that equals, and then it would equal that.
Okay? Does everybody follow?
Yeah.
In other words, if knowing the thing happened does not change the probability, they are independent. If knowing the thing happened does change the probability, they are not independent. Does that make sense? Like, just reasonably make sense? Okay? So let's see, this is our concept. Let's see if it's true here. It says, are black vehicle and van independent or dependent? Okay? So basically it's, help me set this up.
It's
Probability of something given something.
V given B. Well, really with this one, it's you can add it either way.
Okay? So let's do this first one. Let's see if I can scoop this down. Yay. Alright, what does this mean?
Given that
Given that it's black,
if
probability of a van. Okay? So we're here. What's the probability of being a van in that category? 3 out of 13. Okay? What's the probability of being a van overall?
100%. Oh, 3 out of 23. Of being van.
So take just all of the vans, which was 3 out of the total.
22.
So what do you think? Are those independent?
No.
No. In other words, if we know, well, tell me what that means. Knowing that it's not independent, what does that mean for the scenario?
That all of the vans are black.
It doesn't necessarily tell us that. Like, pretend you don't have the data to look at, the table. All you know is that those two probabilities are not independent. So what does that mean about the actual scenario? Did you just say they're not independent?
Okay. No.
Yeah.
Dependent.
The sky is blue. Why? Because it's blue.
Okay. think it's manageable because worms are four.
If I know the vehicle is a van, does that affect whether it's black or not? Yes, it does. That's
Okay,
what that
yes.
means, right?
Yes.
Or vice versa. If I know that it's black, does that affect whether it's a van or not?
Yeah. No.
All right, let's see about the second one. See if we can fit all this in here. Go down. Go down. Thank you. We still need the categories. I think that's good right there. Okay. So now we're going to do R and C. Red and car. Let's see if those are independent. So how do we write this? I need to go back up, but let's write it first. What goes in here? Could we do R given C? Is that what you said?
No, I was going back. I was going like R and
Oh, okay. What has to go here now?
Um,
Is it P of C or P of R?
P of P of
It's got to be the first one, right? In other words, does knowing R affect C? That's what we're asking, right? The main event that we're caring about is the probability of it being a car. So does knowing that it's red affect that, or is it the same as just probability of it being a car? Okay? So let's go back up here. What's this one says knowing it's red, what's the probability it's a car? So, how do we do that? Knowing it's red, what's the probability that it's a car?
5 out of 7.
Okay, that's 5 out of 7. And then, what's the probability of it being a car? 11 out of 22. Are those the same?
No,
Yeah.
Sorry, I'm confused. So if they were independent, it would be the same fraction?
Good. Well, okay, it would be the same reduced fraction. It may not be the same initially, but if we simplified it, it would be. Or if you divided it to a decimal, it would be. Very good on it? Okay, quick question. Would it have mattered if we did this?
that's different.
Let's check. This says probability that it's red, knowing it's a car. Probability that it's red. Okay? So probability that it's red, knowing it's a car is what?
5 out of 11.
5 out of 11. And then probability that it's red,
7 out of
7 out of 22.
It's still not equal.
So did it make a difference which one we checked?
No.
Okay?
Not independent.
That's actually.
Now we have a fairly useful check for independence so that we can determine if we can use the multiplication rule instead of just wondering. Remember we said it's kind of hard to know for sure just based on your gut. So now we can check. All right, let's try this one. So this is junior class at a high school about taking French. Do you guys wish we had French here?
Yeah.
That would be fun to learn, huh?
No.
One of you should go learn French and then come back and teach it here. Corbin. A student from the junior class is selected at random. Let G be the event the student is a girl, and F be taking French. Okay, are they independent? I'm going to let you check that. Okay, you kind of have two options on this. So just curious, how many of you did this first one? This should say PG, sorry. How many of you did it that way? 3. Okay, how many of you did it that way? 3. What happened to the rest of you? Okay. All right, probability, what is this saying? Let's just say it in regular words. Yep, knowing that they're taking French, what's the probability of being a girl? So that is 45 out of 75. And then what is this saying? Probability of just being a girl. So 75 out of 500. Okay? Now clearly those are not reduced. So how do you compare?
It's 300 out of 500.
I did the wrong one, thanks. Not reduced, so you could turn both into a decimal to compare those, or reduce your fraction. I honestly think decimals are faster. So, why is this thing weird? There we go. So 45 out of 75, and then 300 out of 500 is 0.6 also.
So it is.
So are these independent? Yes. What does that tell you about the situation? And don't say that it's independent. Yeah. Specifically, what do we know?
I know that they can maybe girl taking French.
Go ahead, Nate.
I was supposed to just go to say what he said.
I didn't listen to what he said. So I was like, I didn't listen to what he said. What did?
Captain Island. Yeah.
Nate's on drugs today. Be more specific. Specific to this situation.
Okay.
Not a general definition of independence.
That it doesn't matter if you're a girl or a boy. That it doesn't matter if you take French or not.
Yeah.
It does. Okay, being a girl doesn't affect whether you take French.
Yes.
Okay, that's what it's saying. Okay, how many of you doing it a different way got a similar result? Now, are these going to be the same?
No.
No, they're not. Let's do that just to prove it. So, given that we know it's a girl, so this direction, what's the probability of French? That's 45 out of 300. And then probability of taking French is 75 out of 500. Okay, so clearly those two are different decimals than these ones are. This time we get 0.15. So in terms of the test for independence, it doesn't matter which way you do it, it will prove independence either way. But if I ask specifically, what's the probability of taking French given that you're a girl, notice that's 15% versus the opposite, which is 60%. So clearly a difference. Just make sure that you know which question I'm asking. Good on this?
Yeah.
Okay. So far, all we've done is tables. How about something like this, where it's just a description of the situation, like a description of what occurred maybe or something? Notice there's no table, in other words. How do we do this? Well, let's get familiar with what's going on. It says the band's marketing agent conducted a survey to determine how many high school fans the band has. What is the probability that a surveyed student plans to attend and is a fan? First thing you need to know is the word and shows up, and it's going to make you want to do what? Just multiply. Can we? What do you have to ask before you just multiply? Is it independent? And do we know that? No. What were you going to say? That's good. Sorry about that. Okay? So, you guys, I'm always trying to push you to think bigger picture when you're sitting at the exam at the end of the unit and we've done 6 sections of, or 5 or 6 sections of random stuff, and you see this word and, do not just multiply. That's my goal, to get you to think that way. Yeah. Don't just multiply. Okay? Well, again, we have 2 ways. We've seen a weighted tree diagram, or an area model, if you'd like to do it that way. But we also have just rewriting the formula that we just wrote down. This time, do you see how we're solving for the numerator? So how do we get it by itself? Just algebraically, what do? We got to get rid of the denominator, so multiply both sides by p of a. And then the numerator's by itself. That's just an algebraic manipulation is what we call that. Okay? So that gets us here. Everybody clear on how we got to that? Okay? Do I need to zoom this?
Yeah.
We need to take up a fund for you guys with your glasses. Is that better? I don't know if it actually got bigger.
No, right back.
Yeah. Well, it was on best fit. Now it's 150. Yeah, I think that will work.
I still can't see it, you know, it's like so far.
Is that good? Okay. I sort of feel like I'm getting some faces that don't know what we did here. Are we good on this? Please say no if you're not. Okay, we're not. So let's just do it. What formula is this one right here? Look at your notes. That's the conditional probability formula. Okay? So here's what I'm saying that we did. If we want to solve for any one of those 3 things, we can manipulate this around pretty much any way we want. Okay? So if I multiply by probability of A over 1, what happens to those? They cancel. But can I just multiply one side by something? No. So multiply both sides by it to keep it balanced. And now, do you see we have a formula for the probability of A and B when it's not independent? Okay? And so that's what this is here. Not independent and. How is it different than the and probability that is independent? It looks pretty darn close, so what's different?
Well, we also have
Guys, that little line with the A, right? That's literally it. So otherwise it's probability of A times B, but now we have given A occurred. So we have that little change to the formula. Okay. Well, how do we read all this data, this percentage data, to fill this out? So let's go back. Pardon the scrolling, but it says probability that a surveyed student plans to attend and is a fan. So what are our 2 events? Because all we have down here is A's and B's. So we need to decide.
A is the times 10 and B is the family.
Okay.
Well, that's how I read it.
I'll put A for that, and is a fan, let's call that B. Everybody good? Okay. So plans to attend is what percentage? 70% of students plan to attend, so 0.7. Okay? And then the second one, probability that a student is a fan given that they plan to attend. I'm going to actually write that out while you look at the chart. Okay, did you figure it out? What is that? What was it? What's the probability that they are a fan given that they are planning to attend? 80%. It's this group, right? Okay? So what do we do with those two? Do it in your head. What percentage is this?
You pointed at 0.7, and it said 1.7, so.
Okay, I'm just teasing.
70%.
56%. Okay? How'd that go? Are you following? Okay, weighted tree diagram. You want to try setting that up? I would like you to. Yes, I want you to try it. It's a. Alright, you guys have this option. I'm going to do mine sideways. If you want a little bit more visual, our first branch is attend or not attend. So you could do something like this. 70% attend, and then 30% not attend. You don't have to make it heavier towards the higher percentage. It's just a visual thing. Okay? Off of each of those, we have fan or not a fan. So if they're attending, we have 80% fan and 20% not a fan. Okay? And then if they're not attending, we have 25% of fan and 75% not. Okay? Again, I'm just trying to give it a visual with the bigger branches, but you don't need to do it that way. Okay? So this one says, what was the probability that they were going and a fan? So go down the going branch and then the fan branch. 70 and 80. So same thing, right? 56. If I said, what's the probability of not going but a fan? How would that look? Not going, but still is a fan. So 30 times 25, which is 7.5. Okay? So in other words, it's not very likely that they wouldn't go if they're not a fan. That's kind of what that would tell us. Okay? How's that feel? Which one of these do you like better? Okay? And people are pointing both directions. I guess it's probably worth really quick just showing you the area model. So I would do it this way. Going or not. So 80%. So that was 70. Sorry. 70% and 30% not going. Okay? And then in the going category, it was fan, not a fan. So 0.8, 0.2. And in the not going category, it was 0.25 fan, 0.75 not a fan. Okay? So then you just find, like, what's the area of this little group here? Well, it's 0.3 times 0.25. And as long as you're labeling, this is a great way to do it as well. And you saw it took like 30 seconds to set it up, so it's not like it's a ton more work. You're welcome to use any of those three strategies for this. Okay? Whatever is best for you. Grab that sheet. Actually, hold on. We got to go write this on your notes. Okay? We have to write two things on your notes. And then we're done. Test for independence. What am I about to write here? What goes there? If I write P, B given A. Yep. And then we'll say if the two sides are equal, they are independent. This is a, I don't know, hopefully it stands out. Maybe put a box around it, but this is another formula kind of situation. And then we need to write about the and probability not independent. And it's making me wish that I had saved room with the and probability before.
Well, now you know for next time.
Do you guys have any way to squeeze it in? Yep.
No.
I do not.
Oh, wait, actually, yeah.
So I think what I'll do with this,
Because
so I'm just adding this little note, C not independent on the next page. That's how I'm going to take care of that. Sorry that we didn't do that right. Probably need to put another box around that one. Okay, now I will say, let's add to this note, or, actually I don't want to say it that way because that'll look confusing. You can also create a weighted tree or area model.